Well, hello guys. I think we're about ready to get started. Just wanted to welcome you all to this Q&A on storage for Kubernetes. So I'm Paul Sobey. I'm head of product for StorageOS. I've got 20 years doing various kinds of engineering, starting with systems administration work and heading into reliability engineering. Mostly working within the quant finance space in London and in New York. On the call with me is my colleague Janki, who is our head of marketing. She's kindly set this webinar up and will be asking some questions to help with the flow and to give us some structure and to keep things moving.
Hi guys.
So a quick introduction to StorageOS, guys. Where did we come from? So StorageOS is a cloud-native software-defined storage engine. And we'll get into what that means during the remainder of this call. But just before we get to that, where did we come from? Well, our founder, Alex Cherkop, spent time as a storage engineer in various investment banks and spent a lot of time becoming, I guess, frustrated with the limitations of storage that was tied to nodes using traditional applications. Began experimenting with building a software-defined storage engine, and really StorageOS was born from there. So StorageOS is a distributed software-defined storage cluster. We exist to provide persistent storage for containers. Briefly speaking, we've got two sort of main components. We have a control plane, which is what forms a cluster, orchestrates volume operations, and we use etcd for distributed consensus. At the same time, we have a data plane, which is a purpose-built storage engine. Now, this is really, really important in the architecture of StorageOS. So the fact that our storage engine is built from the ground up, and our on-disk format we have some patents on that, allows us an awful lot of flexibility. We're also very, very tightly integrated with Kubernetes. So control over these components together allows us to deliver a particularly well-integrated solution for persistent storage within containers. Now, just a level set as we talk here. We're assuming some basic Kubernetes knowledge. I've tried not to assume too much, and specifically not so much knowledge about persistent storage within containers. So we're trying to keep things very general and fairly basic, just to set the lay of the land. We're going to be talking in very general terms for the majority of this presentation, so not really StorageOS specific, although of course I have my personal biases. But we'll be talking about the just delivering persistent storage to containers within a Kubernetes environment. Now, we've had lots of questions up front, so we're going to cover some of those later on in this presentation. One or two of them are StorageOS specific, one or two of them are general. Apologies for anything we don't cover today. Please do reach out directly. Rest assured that that we'll get to them and reach out directly and work with you to get you the answers that you need.
So why run stateful applications in Kubernetes? Is the first question. Paul?
I think this is a great place to start, and my answer really is summarized in those three words that you can see on the screen. Kubernetes is awesome, so why run anything in Kubernetes? I think really the benefits here, so just backing up. So I think really the benefits, it's just worth sort of emphasizing the benefits of both containers and orchestrators, because the reason that we might choose to run stateful apps is closely coupled with any reasons for running stateless apps. So if we think first of all about all that containers have brought to our industry, a lot of benefits associated with containers, which are probably well understood by everybody on this call. They're immutable. They're easy to deploy, they encapsulate all of our dependencies, They give us a lot of resource efficiency, so we can pack lots and lots of different processes onto our compute nodes very efficiently, and so on. So I think the case for containers has been well made within the industry for some time now. On top of that, when we get to Kubernetes and orchestrators themselves, declarative provisioning. So the ability to express the way we want the world to look using a piece of YAML is incredibly powerful, and dare I say it, pretty addictive. So we don't need to tell the orchestrator what to do, we simply tell it the way that we want the world to look. Speaking as someone who's spent a fair amount of my career deploying applications using more traditional means, the Puppets and the Ansibles and the Salt Stacks of these worlds, those are all great tools. But just deploying applications with an orchestrator is really efficient and really addictive. It's great fun. Of course, orchestrators let us do self-service. So as engineers, I think we all like to move on and get our apps deployed on our own without necessarily needing to engage too many of our colleagues, perhaps on the same team or perhaps in separate teams. So self-service is a real benefit here. Apps deployed with Kubernetes are self-healing. So if we lose a node, we can expect the orchestrator to help us out and redeploy that app elsewhere. And of course, we get all sorts of benefits with horizontal scaling. So why run one app when we can run 10 copies of it? That's often a great answer. It's all very easy. So if you think about the journey, we really see it as having been sold on the benefits of containers. We then move to orchestrators to help us run them. We typically then deploy our stateless apps. I'm sure you guys have all got various web services and middleware and transformation layers in production. And then we reach the question of stateful applications. So what is a stateful application? A stateful app is an application which wants to use disk in some way to persist state. So typically we're talking about databases, relational databases and NoSQL are both great examples here. And also message buses. So Kafka, ActiveMQ and similar buses all persist state somehow using disk. Now, in order to explain why this is important, I guess it's worth pointing out, just going back to what we said about containers. Containers are immutable. So the file systems within those containers can be written to, but anything that we write is going to disappear outside of the lifecycle of that container. So if we want to run a database or we want to run a message bus, then it's very important that we find a way of persisting data outside of the container. And that's really what StorageOS is for. That's why we're here. So thinking about why we would run stateful apps in Kubernetes, some specific benefits. We have less maintenance of nodes outside of our cluster, less patching, less configuration management, so less management of Ansible and Puppet and Salt Stack, CF engine perhaps. We've got the orchestrator helping us out with all sorts of issues of deployment and self-healing. And of course, it allows us to become application-centric in our thinking. So this is one of those great cloud-native principles that we all begin to absorb as we move our workloads to Kubernetes. Thinking a little bit more about the application. Now, in a traditional world, we tied our volumes, our disk space, to nodes, and we would have applications consume those. But in a world in which we can use declarative self-service provisioning, we can tie our volumes to our applications, and that is a much nicer way to think about disk. Disk is just one more resource that an application might wish to consume when it runs. It's also worth noting that this opens up a few new patterns for applications for us. So the classic example that I always use is in the case of a Postgres server. In a traditional world, we might have a Postgres server running in the corner, carefully tended and carefully tuned by a diligent operator, and we might have, say, 100 databases on that server. Well, in Kubernetes, if we're running that app using a layer like StorageOS, we could run those 100 databases inside a single Postgres pod, but we probably wouldn't choose to do so. We'd probably choose to use 100 separate Postgres instances, Postgres pods, and therefore we'd buy into a bit of the horizontal scaling that our orchestrator gives us for free. A little bit less tuning, a little bit less management. So this is just one really, really good example of of why running stateful applications within Kubernetes is great. But ultimately, I suppose if we've moved all of our applications to Kubernetes, all of the stateless ones, we just want to move everything there because it makes sense, right? Kubernetes is awesome. The orchestrator is great. So let's put everything inside Kubernetes.
Amazing. Next question. What are the challenges?
So I think a few challenges here. Other than the fact that it's new technology and we're all getting used to it. For me, it often pivots around questions of workflow. So we're all familiar with running physical machines. I think we're all used to the patterns of deployment and maintenance there. And similarly with virtual machines, not a lot really changes. We use the same techniques, the same orchestration, etc. When it comes to containers and orchestrator, workflow changes completely. So there's an entire life cycle to learn here, from baking our applications into containers in the first place, through to understanding the consequences of their various properties, so the fact that they're immutable, etc., etc. We can't cheat, of course. So I don't know about you guys, but I have from time to time logged into a server and tweaked config parameters, etc. at runtime. All very naughty, but it's something I think we've all done. That's very, very hard in a world of containers. It's very definitely an anti-pattern, rightly so. We need to learn the orchestrator. So a lot of changes in terms of learning to understand how to get applications deployed, etc. And of course, day two operations. So are we managing etcd properly? Are we managing the orchestrator itself? Are we observing? Are we monitoring? Are we reading logs and metrics and things like that? So all these issues of workflow are for me really important because I think as engineers we all learn that technology is relatively easy. People are hard. Is often the way I think about it. So changing our workflow is hard. On top of that, backups, of course, we need to consider. So if we've got stateless apps within a cluster, we don't really need to think too hard about backups. We've simply got some YAML manifests somewhere which describe our workloads. And that's all we really need to do. We can tuck those away in Git somewhere, and that's what we need. In the case of stateful apps, of course, they're persisting their state. Now, the stateful apps are often the sort of the crown jewels, really, of organization. These are the databases which host lists of customers, sort of lots of operational requirement. Often a lot of our IP is baked into our stateful apps. That's where it all resides ultimately. So we need to think very, very carefully about backups, and we'll get into that in a separate slide later on. One big challenge of running stateful apps in particular within Kubernetes is that of upgrades. So we see this come up time and time again at StorageOS. Upgrades of both the orchestrator itself and potentially the storage system. So it's becoming an increasing pattern to have immutable nodes, and rather than upgrading the versions of the orchestrator on them, we simply might want to replace those nodes with fresh versions. Now this obviously presents us with a little bit of a challenge when we have stateful data persisted to those nodes. These challenges can be overcome. We just need to think about it a little bit up front. It's not so hard, but it's worth considering. Okay.
Next question. What applications should we deploy first?
All right, so a fairly simple answer here. It's the same as gaining trust. Gaining trust in the platform is important, and gaining understanding of how to operate the platform. So the short answer is move the least critical apps first, so that we can get some experience. So the order that you might consider doing this, development apps, and in particular, unleashing developers into a stateful environment is great because that allows us to leverage those immediate benefits of self-service and declarative provisioning. So so giving developers the freedom to spin up their own databases within Kubernetes makes a lot of sense in a non-production context early on. At the same time, one of the things that we see an awful lot is CI/CD pipelines. So one of our customers, in fact, spins up many StorageOS volumes a day, because they are building Elasticsearch instances as part of their test and development pipelines to do functional integration testing. So these sorts of pipelines that really take advantages of the flexibility inherent in software-defined storage can be really useful. So those are great places to start. After that, it tends to be applications that are around the edge that perhaps we could do without in a pinch. So instrumentation. So perhaps time series databases like Prometheus and InfluxDB might not necessarily be on your critical path. Monitoring applications, so log ingestion, that sort of thing. Metrics analysis, anything that allows us to gain confidence and comfort in the platform while providing additional value to the organization. Those would be the ones that we start to move first. And then we really just head in increasing order of importance. So in the world of finance, perhaps, tick data and things like that, we might choose to move a little bit later.
Okay. Next question. How can Kubernetes PVCs be used to deliver persistent storage?
All right. So this is where we get into defining a little bit of terminology. So bear with me, guys. You've probably all seen some or all of these terms, but it's worth defining them because they're sort of very much Kubernetes specific lingo. So starting out, we have these two concepts, the persistent volume and the persistent volume claim. Now, these are related, but they're definitely separate logical constructs. So the way we can think about these is the persistent volume represents some piece of usable storage, typically a disk. The persistent volume claim then represents an application's claim on some or all of that disk. Typically, we see a one-to-one mapping between these two, but that isn't necessarily the case. So we can imagine a world in which we had a very large volume with several smaller PVCs taking pieces of that volume. But yes, it's normally a one-to-one mapping. So persistent volume is a disk. A PVC is an application's claim on that disk. Then we have the concept of a storage class. So a storage class really enables us to map a class of storage within Kubernetes. Now, typically this maps to a particular provider, so a particular route through to storing some data, but it also allows us to experiment with some parameters. So we might define different storage classes for a particular provider, but perhaps iterating on parameters like whether we want HA, replication, encryption, that sort of thing. So a storage class is simply a class of storage. The clue's in the name. And then what we get to is the stateful set. And I really wanted to call this out explicitly because we see a lot of confusion here. So there are several controllers within Kubernetes that allow us to deploy apps. And the most commonly known is the deployment. Of course, deployment allows us to ensure that one or more copies of a stateless application are running. The stateful set is the controller, which is really designed from the ground up to run stateful apps within Kubernetes. So it's purpose-built. It's really important that you know this, guys, because we see many manifests, a lot of prior art on the internet, which uses deployments for stateful apps, and it causes all sorts of pain further down the line. Yeah, it's just worth noting that. So what does a stateful set do? Well, it allows us to run one or more copies of a stateful application within Kubernetes, and it allows us to provide guarantees about the ordering and the uniqueness of those pods. So we can say that we would like to run one or more replicas of our application, and we can provide a template for the volumes, for any volumes that the application might use. Now, the key thing about that template is that stateful set members will always have an index, a numeric index, and our volumes will be we'll get a guaranteed unique volume for each instance of our stateful app that runs within that stateful set, and that will persist through the life cycle of the stateful set, irrespective of where that particular index happens to be spun up within our cluster. So on the right hand side, I know it's a little bit hard to see. We've just got an abridged version of some stateful set YAML, just for you guys to see and point out a few salient points. You can see in the bottom left that there is a link to our GitHub page from where I've pulled this. So no need to panic if you can't read the words on the screen as they stand. But what we have here is a stateful set definition. So we can see we've got the API version and the kind defined as stateful set. And in the specification, it's a bridge, so there's a few dots there, but you'll note that in this particular instance, we're going to run one of them. And the template for the stateful set, in this case, it's a Postgres pod running, and this is the Crunchy data distribution of Postgres. So our friends at Crunchy, who we work with a lot, provided us with this with this container. And what you can see is that we've got a volume mount defined as being plugged in at a specific path within that container. So this is really sort of how we can think about presenting persistent storage to containers. We define a mount path and we plug that persistent volume into that specific path. You'll note there's a config map defined as a way of plugging config in. We'll get into config maps shortly. And at the bottom then we have the volume claim template. So this template is going to be reused for every single one of these these replicas as they spin up. So in this case, it's a 5 gig volume using the StorageOS storage class. So when we run that stateful set, we're going to create a volume and spin up that Crunchy data pod. And it's as easy as that.
Great, thank you. So Kubernetes talks about persistent storage. Do I just need Kubernetes?
Well, the short answer to that is no. You need a bit more than that. Having said that, Kubernetes does provide us with a couple of constructs that are useful to experiment with the concepts of persistent storage. So I've linked to the docs here, guys. You can click on these and read them at your leisure. There's the empty dir. So this allows us to bind effectively an empty directory within an application. We can back that by the disk or tempfs, and that will exist purely for the life cycle of the pod. But it is a fast way of getting some scratch space for your applications while they run and using the node storage. So it's worth considering. Moving on then, we have the host path. The host path definition, and in more recent versions of Kubernetes from 1.14 onwards, we of course have local. And both these are ways of provisioning directories on a specific Kubernetes node and allowing us to then consume that from within our application. Now, the important thing to note about these constructs is that they're restricted to one node. The data it exists only on one node. It's not replicated, and it's only consumable from that one specific node. So it's great as a toy. It's great for experimenting, but definitely not suitable for production use. That data is not consumable from elsewhere in our clusters.
Okay, thank you. The next question is, what are the considerations for selecting a persistent storage layer?
Okay, there's a few things to think about here, and they all sort of depend on the proclivities of the admins in question who are looking at this sort of stuff. I would say that ease of use is important, and by ease of use I mean ease of everything, I suppose. So ease of understanding the concepts, clarity, ease of installation, ease of maintenance, etc., etc., etc. So we really want the world to be easy and clear. Observability is very important. We should think about logging and metrics both. So observability is important because as admins we are really charged with running production plants. We've all had the 3 a.m. wake-up call, I'm sure, and it's really important to know that when things are going wrong, that we can figure out what's going wrong, but also that we can really reason about the steady state operation of our cluster. So good logging, can I follow the path of a volume? Who created it? When was it mounted? Things like that. What sort of metrics do we have available? One really fun advantage of software-defined storage, and something that we talk about a lot at StorageOS, is our Prometheus endpoint. So the ability to get volume IOPS and volume bandwidth on a per application basis is really game-changing in my view. If you've ever stared at an IO top window and tried to figure out what proportion of IOPS are coming from a specific application, you'll understand the pain there. So observability of our cluster, both steady state and under duress, I think is important. Next, we get to performance, and it's worth talking about this a little bit because we get asked a lot of questions about storage performance. Benchmarking and reasoning about storage performance is tricky. There's no getting around it. And reasoning about it within a clustered environment is even more tricky. So some things to think about here. We should define the difference between latency and throughput. So throughput is simply how many bytes a second can we get into our application. Latency is how long does it take a given IO to complete. Now, the interesting thing about latency is we can take an average, but of course, as engineers, what we really want to think about is in particular with storage, is the 99th percentile latency. So I'm not just interested in how long a particular transaction takes, but I'm interested in how long all of those transactions take. Because when I'm running a database, perhaps if I've got a website backed by a database, I really want to be able to understand that and to be sure that all of my transactions will be complete within a definable bounds. So watch out for tail latencies would be my advice here. We should think a little bit about synthetic benchmarks. So we can measure the performance of our storage application using a couple of techniques. We can use synthetic benchmarks. The one that we use internally at StorageOS a lot is FIO, and we can tune FIO. We can ask it to run workloads using different block sizes, different queue depths, different compressibility of data, etc., etc. So we get a lot of control there, and we should really, when we're considering the performance of a storage layer, we should iterate on those parameters to get a real sense of how the storage performs under different workloads. Watch out for compressibility with software-defined storage in particular. As data becomes more compressible, typically we can move it around a lot faster. So compressible data, it's a great thing to test how your storage engine performs using compressible and non-compressible data. Moving on then, the final arbiter of performance for any storage application has to be how fast does your application run. So regardless of any benchmarks or any throughput measurements you may have made, the important question is how many widgets a second can my database ingest? How many queries a second can I make to this Elasticsearch cluster? How many objects a second can I push through this Kafka bus, etc. So always, the final arbiter must be run your application and measure how fast it goes using a representative workload. So typically a message bus, for example, will run at different speeds depending on what sort of data we put through it. So make sure it's representative. And finally on performance, make graphs. So it's one thing having a kind of a snapshot of a number, but what we really want to be able to do is measure a time series of performance across a minute or a 10 minutes or a half an hour period, just to make sure that that performance is nice and deterministic, nice and consistent. In particular, you really want to watch for any cache warm-up times at the beginning, the sorts of things that it feels like it's going very quickly and then it tails off, etc., etc. So time series databases like Prometheus and Influx allow us to plot the performance across a few minutes and then to reason about it a bit after that. We should think about support. So I think if we've decided that the crown jewels of our company, this stateful data that we're going to put into a product, we really want to make sure that when things go wrong, that we have a good support partner, both during installation for recommendation and then who are we going to call at 3 o'clock in the morning when things go wrong. You really want to make sure that you have a good partner there, and think about when you call that support organization, who do you get through to? I think we've all waded through several tiers of engineering to get to someone who sort of has a decent answer. So how accessible are the engineers within this support organization? How quickly can I get access to somebody who knows what they're talking about, who can help me with my problem? We should think a little bit about high availability. So high availability is defined as if I lose a node, I would like my data to carry on carry on being available. Now, typically we can use synchronous replication here to help us, where we can replicate our data between several different nodes and make sure that if a given node goes down, that we can move things around. Several storage providers, including StorageOS, of course, will deal with this very seamlessly for us. We should think a little bit about encryption. So our threat model here are bad actors, either listening to our traffic on the wire, or perhaps gaining access to our disks, our OS instances, or perhaps just driving a truck into the back of our data center and wandering off with our disks. But either way, I think it's important that for certain volumes, for certain applications, we can be very, very sure that our data is encrypted and is locked away. Further, we should think, so I've got a couple of extra notes here. We should think a little bit about access topologies. So storage within Kubernetes comes, I guess the beauty of software-defined storage is that it's incredibly flexible and allows us lots of different topologies to play with, and they all have pros and cons. So starting with hyperconverged, the hyperconverged model defines where our data can exist anywhere within our cluster. Any of our nodes can provide access to that data, and the storage can be consumed from any node within the cluster. Now, this offers us the enticing prospect of locality, where for certain workloads, we might want to ensure that our application pod runs on the same node as our storage. What that means is that we don't have to traverse the network in order to get access to our storage. So for certain applications, that's going to give us a really big performance boost. We can have a think about the placement, the flexibility of placement of volumes as well. So how easily can I vector different groups of volumes around within my cluster as it grows? Then we have the sort of hybrid model. And the hybrid model is where we can consume storage from anywhere within the cluster, but we perhaps want to restrict its serving to sort of 4 or 5, to a subset of nodes within the cluster. So that's hybrid. And then we get the so-called multi-cluster patterns. So for various different reasons, multi-cluster is an increasing trend within the industry. Perhaps we want some centralized storage nodes where we can consume the storage from outside. Perhaps we want to replicate data between different clusters, etc. So think a little bit about access topologies, both what's possible now and what you might like to do in the future. I think one important consideration when selecting a layer is how much you would like to be agnostic. So of course we know that all of the major cloud providers have excellent persistent storage offerings. That's great. It might be of additional business value for us to consider whether we can deploy an agnostic layer to give us a little bit of flexibility and avoid some lock-in there. So it's certainly worth considering. If you're on-prem, if you've got data centers, etc., and you've got a pre-existing investment in storage hardware, then consider if there's an easy route to consume that. If you've got a filer or a SAN, then perhaps there's ways to connect those and consume those from your Kubernetes storage. So lots of different considerations there. I've tried to be deliberately general and agnostic in my commentary here. Loads of things to think about. But I would say that the ones on the slides are the important things to consider. So ease of use, observability, performance, quality of support, high availability, and encryption.
Great, thank you, Paul. Next question is how to migrate stateful apps from legacy to container.
All right, so this is a great question that was submitted by one of our listeners. And we see this a lot because, of course, in an ideal world, in an ideal cloud native world, we would all be rebuilding our applications from scratch to be fully cloud native. Of course, that's not reality. As administrators, I think we're charged with living in the world as we find it, not as we would like it to be. So there are lots and lots of applications within enterprises which aren't necessarily going to get rewritten, but that we would really like to move into a container and by extension into Kubernetes and an orchestrator. And of course, a lot of those applications are written with the expectation of consuming disk. So by using a stateful layer within Kubernetes, we can migrate a lot of those applications very quickly and very easily into Kubernetes and gain some of those benefits of the orchestrator. So the steps are pretty simple conceptually. Any application can be put into a container, of course. We can simply construct a Docker file for it, and we can build a container. So lots of instructions, lots of tutorials on the web as to how to do that. Nice and easy. What we should think about then is the configuration. So this is where we get back to config maps. So remember that once we've built our application into a container, we need to remember that those containers are immutable by design, really wanting to enforce good workflow and good practice. So by extension, don't bake configuration into your containers. It's just such an anti-pattern. Kubernetes gives us a great way to deal with this, the construct of a config map. So a config map, I'm sure you guys are familiar, but just to reiterate, a config map is a set of key value pairs that we can express in our manifests. They exist as a first-class citizen as a Kubernetes object. And those key value pairs then can be rendered into our container and rendered to our application in various different ways. So they can either become environment options, they can become command line options, or they can be mounted into the container as read-only files. So by combining putting our application into a container and then using a config map, we can get the benefits of running things in a container while giving ourselves plenty of flexibility regarding using configuration, defining configuration. And then of course, all we need to do from the storage perspective, it's very simple. We determine which mount points we might like to make persistent outside of the lifecycle of the container. So /data or /srv or whatever we choose to use. And for each of those, we define volumes and we add them to our manifests. So very, very simple in concept. And we see a lot of our customers doing this. A couple of extra considerations for you. It's worth considering HA. So it's worth considering for these legacy applications if having them fully HA and managing replication is important. The answer is almost always yes, but it's worth asking the question. And secondly, it's worth considering shared file. So by default, the default access mode for Kubernetes volumes is read write once. That implies a one-to-one mapping between an application and a volume. But for certain applications, they're really written with the expectation of sharing state in some way across multiple copies of that application using a file system. So I think we've all seen the file system as a message bus pattern. It's not a particularly pretty pattern, but it is very, very common. So do consider whether when you deploy a legacy application into a container, do consider whether shared file is of benefit to you. Now, of course, shared file often incurs a performance penalty. So again, it's worth asking the question. Don't make it a default, but do consider it.
Great. Thanks, Paul. The next question is, what are the backup strategies for persistent storage in Kubernetes?
Okay, a few options to consider here. I'm going to talk about the data first, but of course, it's also worth considering the metadata and the application definition. So we'll get into that shortly. Typically, with stateful applications within Kubernetes, the sorts of applications we're talking about are applications which don't necessarily like having their file systems backed up directly. Databases are often moving targets as far as a file system is concerned. So the first answer from my perspective when backing up any application is there a backup API? Can I get the data out of the application using its own native APIs? Now for MySQL, we have MySQL dump, and for Postgres, we have PG dump, etc., etc., etc. There's always routes to get the data out efficiently. Or in some cases, to ask the application to perform a backup to its local file system. So that's consideration number one. Can I ask the application to deliver me the data? And if not, can I ask the application to quiesce so that it's safe to take a copy of the data? Now, one pattern that we see a lot, and we have recipes on the StorageOS website for this, is if we want to get access to the underlying file system data for whatever reason, then we can simply use sidecars. So we have some recipes for this on the website. it's very easy to orchestrate a sidecar that exposes the data and the underlying volume in various different ways. So rsync is obviously a great choice. SFTP perhaps Nginx, so that we want to serve the data with HTTP, etc., etc. So presenting access to the file systems as they're mounted is something that's fairly easy to do. At this point, I just want to reiterate something which comes up at shows and conferences an awful lot. Question we asked: can I take snapshots? Snapshots are absolutely a useful tool, but they are not the same as backups. So, guys, please ensure that that when you're thinking about backups, you aren't thinking only in terms of snapshots. I've personally seen situations in which snapshots cannot be restored because because snapshots were taken on inconsistent databases, and it's not fun. So that's really what I've got to say on backups. I will say that as the industry evolves and patterns evolves, the notion that we might like to get access to the data of many volumes at once to sort of back up entire clusters, that notion is definitely evolving. So watch this space, really. It's also worth mentioning metadata. So if you may remember at the beginning, we talked a little bit about the importance of application-centric storage, thinking about binding our applications and our storage quite closely together. Well, if we're going to back up data, then it's really good to think about backing up the application definition at the same time. Now, tools like Veeam and Valera are really good here. So they really help us do that. And of course, StorageOS realize that we have our part to play in terms of integrating like products with products like these.
Cool.
So hopefully that's a little flavor of backups.
Thank you. The next question is, what are your thoughts on multiple Kubernetes clusters in one data center?
That's a great question. And I think we can probably extend it by implication to multiple data centers as well. So as an industry, the patterns here are still really emerging. Ways to link Kubernetes clusters at any level are still very definitely evolving. Now, the reasons that we might want to consider multi-cluster, two big ones, I think. We might consider the blast radius. So if something goes wrong, perhaps with our etcd or with our masters, it might be nice if we can have a little bit of segregation there. And secondly, for commercial or operational considerations, it may make a lot of sense to deploy multiple clusters to ensure that perhaps a subset of administrators have access to our production applications, etc., etc., etc. So there are good reasons to stand up multiple clusters. One we see at StorageOS a lot, a request that we see a lot, is the ability to consume storage using satellite clusters from a satellite through to a centralized one. So all these patterns are still emerging. Now, there's some challenges here. So maintenance of the metadata, so making sure that application definitions and sort of objects within Kubernetes are still in sync, and of course migration of the actual data. So it's really early days here. Lots of people are discussing this. It is possible to achieve at an application level some sort of synchronization, but the tooling is all very early. Now I've mentioned KubeFed here. You can see on the link. That's an alpha currently. So the notion that we might want to federate Kubernetes clusters and have links between them is very early. But this is the way the industry is going now. Needless to say, we're thinking about this and discussing this very actively internally. So that's thoughts on multi-cluster.
Thank you. Oh, sorry. So now we come on to more StorageOS specific questions. Looking forward to resizing of volumes, where does this fit in with StorageOS's roadmap?
So we don't want to get too much into roadmap conversations here. That really isn't the purpose of the Q&A, but we did think it was worth just calling this particular question out because it really is our #1 requested feature. So as you guys may be aware, we're currently preparing a new release. And I don't think I'm giving too much away to say that this is really top of our list when we get that release out. So real soon now, I think might be the way to express this. Great. We know it's important, and we know that you guys want it, and we're going to build it.
Amazing. Next question. Major cloud providers have native offerings for persistent storage within Kubernetes. Does StorageOS give any additional advantages in those environments?
So this is a great question. All of the major cloud providers, of course, have persistent storage offerings, and they're all of excellent quality, varying feature sets, etc. I think there are a number of ways in which StorageOS can add value on top of that. So we've already mentioned the notion of being agnostic. So the notion of an agnostic storage layer, I think, has a lot of value where we perhaps want to avoid lock-in to particular vendors or particular technology. We can be application-centric. So the cloud provider volumes, it's often more efficient for us to provision a large volume to a node and then to chop it into smaller application-specific pieces. So being application-centric is and agile in terms of things like volume attach times, I think is something that we can really help with. We can, of course, replicate data across availability zones. That can be a challenge. So the ability to synchronously replicate and ensure that you have copies of your data spread across AZs is great. One interesting artifact that we see an awful lot when running StorageOS in all major cloud providers is we often see quite a significant performance increase for workloads. And there are a couple of reasons for this. The first is that typically there tends to be somewhat of a correlation between performance of volume and size. So bigger volumes often come with more IOPS, as an example. So if we can provision large volumes to our nodes and then chop them into small pieces, then we can take advantage of that performance. Plus, the various special source within the StorageOS data plane, our compression and our caching and the way we move data around, etc., really can give a big speed up for certain workloads. We see this fairly commonly, so it's certainly worth experimenting. And finally, I'd like to mention encryption. So again, all of the major providers, of course, have encryption offerings, but critically, you as the user don't necessarily get to keep control of your own encryption keys. So where you want to be super sure that your data really does remain within your own hands, and perhaps isn't subject to discoverability laws and regulations within particular regions, keeping control of your own data and ensuring that it's encrypted using keys that you keep your hands on, I think is a really important consideration.
Great. The next question, how are StorageOS going to deal with Helm 3?
Okay, this is a great question. It comes up a lot. So in short, if you guys are almost certainly familiar with Helm as a way to deploy applications within Kubernetes, I'm sure. Helm 3 recently G8, and the Helm 2 and Helm 3 manifests are not entirely compatible. So it's going to be very challenging for us to maintain a manifest which can be used in both versions. And we recognize that both versions are going to be out there for some time to come. So what we're going to do is very simply maintain a separate branch for Helm 3, and that chart will be available. I've mentioned the GitHub issue here. You can see on the screen where we're tracking this. So we're going to maintain a Helm 3 chart in parallel with our Helm 2 chart, and we'll switch the defaults over at some appropriate moment.
Perfect. Cool. The next question is, how can I try StorageOS?
All right, so important to note. So StorageOS comes with a developer license, and that is forever free. So it's not a trial. It's a free product. We want you to use it. We want you to like it. It comes with 5 terabytes of storage and can run with up to 5 nodes. And we've got our HA engine built into that as well. So very easy. We've got some documentation on the website. It's very simple. You simply install our chart and our operator, and then you can install the cluster. It's very, very easy. So lots of documentation on the website, including a self-evaluation guide, which walks you through the steps in one simple doc. And I would like to say at this point, very easy, do join our public Slack channel. You can come and engage with all of our engineers on the public Slack channel. We're very friendly, and we'll happily walk you through the process and answer any questions. Worth mentioning at this point that in terms of commercial relationships and pricing, simply email us at that email address, info@storageos.com, and we'd be glad to talk further. So thanks, guys. Thank you for your attention. Thank you for listening. Do want to just reiterate, if you've submitted any questions during this session, or you want to follow up, there's my email address. I'm Paul Sobey. If you want to get in touch with me, I will absolutely be glad to engage on any issues involving storage and Kubernetes. So thanks for listening. It's been a pleasure. I'm sure we'll talk again soon.